Sanku. Quickly touch upon some of the basic concepts involving this area, platform observability and infrastructure closed loops. So I work in the network platform group within data center group in Intel. Here's a legal disclaimer, and thanks to the team to make this happen. So pretty briefly, these are the three main areas we look into: platform observability, service assurance, and transition into closed loop automation. At a high level, platform observability and service assurance, right? So from a telco standpoint, this presentation is geared from a telco standpoint. Observability, in the sense, you hear this term a lot in the cloud environments. Observability is the ability to expose the state of the platform to ensure your service level objectives are met. So this can be achieved by mainly three things in the observability context: logging, metrics, and tracing. However, in communication service provider context, you often hear this observability concept in terms of service assurance. Service assurance kind of covers both monitoring and observability. And whenever you talk about service assurance, you refer to the fact that FCAPS, which is faults and configuration, accounting, performance, and security, those are the attributes that you would look into in understanding the state of the platform. So basically, the idea of service assurance is nothing but an application of set of policies to ensure your service meets the certain service level objectives and service quality level. So in this presentation going ahead, I touch upon the aspect of observability and service assurance together and how it evolves into what we're looking at today, which is closed loop automation. So if you look at service assurance, these three have been traditionally the important aspects for any service assurance system. One is monitoring. Basically, this is where you provide a deeper management and tracking interface. You get a lot of metrics. You get an idea of the state of the system. Presentation, which reflects your reporting, trending, analysis, and ability to understand the state and take corrective action accordingly. And then, of course, provisioning, which is your configuration changes based on predetermined policies to ensure that you meet your service level objectives. So if you look at HC NFV model and track these three areas, so at the bottom you have NFV infrastructure, you have compute storage network, and there are a lot of platform telemetry that you'll be getting out, and a lot of metrics from each of these areas. And then you have your virtualized layer, your traffic, network traffic telemetry, on top of which you have application telemetry, and then of course you have your state of your system, right? So, and a lot of these metrics, each of these can be easily anywhere like 1,000 plus metrics across each of these layers. Now, getting all of these into a common database and running some sort of analytics on top would become key for your service assurance deployments. And once you have this, understand your state, correlate it against your policy, against your end goal, end result that you would want the system to be. And that's where your guidance agent or your policy agent come into play. So I'd cut it out and dig deeper a little more into some of these layers to give you a better understanding. Right, so rest of the presentation assumes so we use this monitoring agent, CollectD. Our team has been actively involved in the CollectD community. This is a monitoring agent that's used by many telco and comm service providers. This agent has been open source for a while now, and it's widely adopted, and you can configure the collection interval. There are a lot of metrics that you could get and export it out to the system onto a remote node, various plugins that you can add and leverage on top of the CollectD, plugins for hardware, plugins for application, so that you get your set of metrics that you're looking for. So here's a snapshot of how the telemetry exposure, at least from the platform level, our team and Intel in general is been very active in. So it's a busy slide. Probably you can start from the bottom. If you look at compute, network, and storage, there's various technologies out of which you can get the state of the platform. In terms of compute, you can look at the RDT, Resource Director Technology, that Yasser just presented. Get the state of the system using these metrics. Run Sure Technologies, which is your RAS, reliability, availability, and serviceability metrics. And if you look at network, on top of the platform, your virtual switch and NIC counters, and IPMI for out-of-band management, PMU, which is your performance management unit on top of your hardware, a lot of metrics from here, and storage, RAID, NVMe, SSDs, etc. Right, so the green indicates some of the work we had already done in upstream. The purple indicates some of the work ongoing. So now you have a lot of these metrics. One, getting in band is something your virtual machine or container application, bare metal application can leverage. Out of band is another concept where you could get through IPMI or Redfish, where you can export this telemetry remotely. So that's another way you can look at getting this telemetry. A lot of legacy systems use SNMP. That's also an integration that is available. And with current cloud systems, you have, for example, OpenStack is one of the popular orchestrator. You have integration into a lot of these processes, OpenStack services like Ceilometer, Noki, AODH, Vitrage, etc., where it exports these metrics and takes corresponding corrective action. And with respect to cloud-native type environments, you have Prometheus, which is a popular monitoring tool for Kubernetes, for example. Have integration, for example, with CollectD with Prometheus, where you can get snapshot of your bare metal node, the metrics from the node. And then if you're someone who cares about streaming telemetry, you have integration with Kafka, which is again another popular streaming telemetry agent that you can leverage to get the metrics out of the system. So now going into the closed loops, right? Now you just saw the amount of metrics. I mean, if you look at here, if you enable almost all of these metrics right here, you're looking at more than about 1,000 plus metrics. I think you cannot see my pointer. Yeah, so you can see almost all of these. You're looking at about 1,100 metrics easily, just with the defaults. Now, once you have this telemetry, what do you do with it? And that's where the concept of closed loop automation comes into play. Here, the idea is you have, this is taken from one of the blocks from PNDA, which I'll touch upon going ahead. So the idea is you can look at broadly three types of loops that to categorize. One is your long loop, which is your offline processing, where you get the telemetry, analyze, and feed it into a remote system, which is looking at planning and provisioning, and then you orchestrate, take the corresponding corrective action. And this type of closed loop is used for these use cases like planning and placement purposes. But then again, with the way the real time and the fast responses are required, what we are looking at is two different closed loops, which is near real time and real time closed loops that are close to the platform, close to the individual compute node. And real time is generally something you're looking at your security and service assurance constructs. And on this one, the near real time is more like an online processing where you're looking at traffic engineering, network optimization. These are some of the use cases that you can leverage. If you consolidate this and correlate it with the existing architecture across manual layers, right, across HC and FE layers. So this is how your architecture would look like, right? So you have the base platform here, and a lot of traffic going in and out, a lot of telemetry going out, but then it goes into your telemetry or storage system on top of which you run analytics, and this feeds into your business layer, which is your OSS, BSS traditionally, and based on the policies that are set here, it translates into your manual layer, and which is generally your element management system or your VNF manager. So SDN layer is also an additional one where you're looking at based on the telemetry, you can take corrective actions at. And so once the policies are kind of determined here, the corresponding actions would be translated to your node using your VNFM and that is where your platform node comes in. So this long loop, or where your telemetry and analysis or analytics is done on a remote centralized node or a remote node, is generally a long loop, right? So, but if you look at 1 second or tens of seconds based corrective action, that's where the concept of real-time, near real-time comes into play. This is where we're doing some of the work with respect to exposing the platform telemetry into something called local platform agent, right? So resource management daemon that Yasser touched upon is one such example, where the policies from your higher layers are sent to your local node, and based on the telemetry, within seconds or less time frame, you're acting upon changing, you're taking corrective action on your local node. I'll go into one of the demos as just an example as how this might work for you. So from our team's perspective, we've been very active in these areas, platform telemetry and local platform agent, and basically this whole area, how to integrate in across the NFVI layers, right? So if you decompose the stack a little bit in a different way, if you look at any networking stack, right? So your hardware and data path across these standard layers, data path and OS. On the top, you have application layer, orchestration, analytics layer. So if you're on the top, you're considering closed loop on the top, and this is where you have reaction time will be across minutes or hours or days, and which is still okay, which is necessary, it's still okay, right? These are some of the closed loops, and that's where the frameworks like PNDA and Acuma's AI. PNDA stands for Platform for Network Data Analytics. It's a project under Linux Foundation for Networking, LFN. That comes into play where you're looking at processing big data and huge amounts of data to take a corresponding corrective action. And Acuma's AI is another project which is recently under Linux Foundation. Again, here, I think it was first open sourced by AT&T. The idea here again is you have huge amounts of data and a lot of analytics and machine learning, artificial intelligence frameworks. How would you bring together all of these components? So Acuma's AI helps achieve that, helps you provide analytics and corrective action over there. But as you go close towards the hardware, actual nodes, right? So you're looking at the control in terms of seconds or minutes. And this is where some of the frameworks, like, for example, for cloud-native environments, Prometheus is a very popular one where you're looking at exporting telemetry, automatically detecting your cloud-native deployment for various metrics, processing them, and then taking corresponding like alerts and corresponding alert functions, alert handler functions, etc. And then also there's eBPF, Evolved Berkeley Packet Filter, which is looking at adjusting these closed loops and basically detect, analyze, and take corrective actions across your operating system layer. Right. So, and if you go down respect to microseconds, for example, this again, like you have your accelerators or your hardware corrective functions based on the state of the system. It can take corrective action. For example, this area in RAS, the run-sure technology detects the failure in any of the memory pages, and if it reaches certain threshold, it offlines certain bad memory pages and ensure the new fresh data is fetched upon. It's just one example of how you can look at microsecond or lower level. So, what does this mean? How does this apply to your use cases? So this is where if you kind of map the architecture into business use cases, in terms of security, you have like a fast threat detection or for fast threat response as an example. Or you're looking at your customer experience. In here you can look at various use cases. Just for example, listed here like your self-service healing or self-healing, auto-scaling, differentiated quality of service, edge placement. All of these come under your improved customer experience. Or if you're looking at your optimization and efficiency use cases right here, capacity planning, optimization, cloud configurations, all of these fit into in this category of where you can automate a lot of these processes to help you provide these use cases, right? So that's where these applications would translate rules to your NFEO, which in turn gets translated into your VNFM, may it be OpenStack, may it be Kubernetes, or any orchestrator you're thinking. Whether you're on-premise, or cloud, or edge, core of your network, in some form or shape, you can look at leveraging these use cases using some of the automated interfaces. And for example, if you go into ONAP, ONAP is looking at an NFEO layer, automating in terms of closed loop automation for policies at this layer. And some of the work I'm personally involved is in OPNFV community, where you're looking at automating these policies across your infrastructure layer, NFE infrastructure layer. So maybe I could show a small demo just to give you an idea. While analytics and like machine learning, artificial intelligence is a common terms that you hear these days, but even without those, like having a condition action rule pair based events and policy processing, show you a demo of how resiliency is something that you can look at in a closed loop fashion, right? So the idea here is we would inject a set of memory faults on the memory used by your DPDK application, for example, and how would you correct and automate in such a way that your service has minimum downtime. Basically, you're maximizing your service availability, right? So this demo is kind of workload agnostic, but what we have here is a virtual border network gateway as a workload. And what we do is we have Kubernetes to orchestrate two instances, one in active mode, one in passive mode or standby mode, two VBNG instances in two containers. Both of these have SRIOV virtual function bindings, so they're utilizing SRIOV VFs and having a DPDK-based application running in them. That's step one. And step two, you're injecting a set of errors. You're using MC Inject as open source tool to inject errors. Now, the idea is based on the rule set that you have defined. You would send in the errors information notification via collectd to Prometheus, and you have basically Prometheus alert handler script here that is looking for notifications from Prometheus Alert Manager. And based on the alerts that, hey, a certain memory error has occurred, it would switch the live traffic from active instance to standby instance. So you could look at doing this in multiple ways. For example, you can put a load balancer in front of it, or you can come up with some cool use case. But here's an example where you have your port bindings, etc., and all you want to do is in a HA mode, you want to switch to your standby container and ensure that service continues working. So let me switch to the demo. This demo is posted on Intel Network Builders, but this is just to give you an idea what it can do. This is the basic UI, user interface that you have. So you have two instances here, active and standby. We haven't started the traffic yet. And active instance A is running on these particular cores, core 1 and 3, and its siblings, I think it's 61 and 59, right? So basically it's running on these 4 cores. Now, as we start the traffic, we would inject 2 pairs of errors, like we would inject 3 errors, but in our case, our threshold is 3. Until 3 errors, your application is still okay. Your 3 errors does not really affect your application. But once it crosses the threshold of 3, which is 5 error case here, once we inject 5 errors, we would see the switch over from active to standby. What you have here is just an idea of the current state of the platform. Here you will see 2 VBNG pods, containers running inside these 2 VBNG pods. And here you have Prometheus alert manager, where you see the logs of Prometheus. And here you have alert handler, which is running on your second node, which is listening on this port for these notifications or errors. And you have telemetry via collectd, which is your DPDK telemetry, basically collecting these metrics every second so that you get an idea as to state of your DPDK application. And you will see here in the Prometheus window, to make it simple, I'll drag the videos to easily explain. In your Prometheus window, you will see the pods, like the traffic is 0 at this point. You have VBNG containers on socket 0 and socket 1. So one main thing in the demo is when you're switching from active to standby, it's NUMA enabled. So basically any memory used by this instance is using NUMA 0, NUMA node 0, and this instance is using NUMA node 1. So basically, if you inject error here, it will switch to NUMA node 1, essentially ensuring that you're utilizing two separate NUMA memory nodes. So from that sense, like this is running on socket 0, which is NUMA node 0. This is running on NUMA node 1, which is your socket 1. Kind of easy to distinguish based on the numbers. So now, as we start the traffic, you will see started traffic coming through VBNG instance A as time goes by. And we'll also see the statistics in the Prometheus. Basically, collectd is exporting the DPDK telemetry to Prometheus, and you'll see the RxTX counters go high. You'll see the values updating here. Yep, so as you see here, the Rx and TX values for these two containers is pretty high. As you refresh, you will see the stats being updated. And so right now, we will inject 3 errors. Yep, so as you click on the 3 errors button, you will see the notification with the severity is warning. All right, so for this system, that there has been memory errors. All right, so this alert goes out from collectd to Prometheus, but then the rule is that 3 errors is still okay. So you won't see any change in the way the traffic or the application behaves. See a minor difference in throughput here with the errors, but then it's not major enough that you should switch over to standby instance. And okay, let's play this. So yeah, this is 3 error case, and let's do 5 errors. I'll come back here. So as we click on the inject 5 error button, you'll see the socket being highlighted, saying, this node is pretty bad, as in there are quite a few errors. And so you'll see the instance switch over to the NUMA node 1 or socket 1, and it's utilizing these 4 cores, and the traffic pretty much moved on to this instance. And the amount of time it took for this switch over is about 4.9 seconds. We did multiple runs, and it's anywhere from 3.9 to 4.9 in less than 5 seconds. The whole goal and the idea is to reduce this time so that you have pretty much real-time type of switchover of the traffic. And you would have seen a bunch of notifications going up here and collectd and onto your alert manager. And then this is listening, alert handler is listening on this port, and which triggers, firing these scripts to switch over the service. So that pretty much changes the traffic gen from first instance to second instance and ensure that the second instance is active. Right, so as we look here and as we refresh telemetry for these DPDK instances, now you see the switchover of the traffic from these active instances to the instances in the socket 1, as an example. So that's pretty much a very brief demo as to what closed loop automation could do for you. Let me close by just going through the last 2 slides here. So in terms of use cases here, right? So this is pretty much essential if you're looking at 5G network slicing, where you're partitioning the platform resources across various slices. Right? So if you see here, it's the same underlying infrastructure for 3 varieties of usages: your low latency usage versus machine-to-machine communication, etc. So how would you achieve this level of resiliency or this level of so closed loop automated ways is only through automation, and that's becomes a crucial part of it. That's the only way you can provide service assurance required for all of these slices. We had considered quite a few use cases and working on some demos. Basically, demand-based energy savings. One of the example demo that we're working on is, for example, any DPDK application, it utilizes 100% of your CPU. How would you ensure that the power of that CPU core can be high or low? I mean, even if it's not doing any traffic processing, it would still continue to consume 100% CPU. How would you leverage whether you want to increase the power to that core or reduce it? So that's an area that we're looking into. Workload resiliency, as an example that I just provided, noisy neighbor detection, avoidance. For example, from afternoon talks from Yasser, Research Director Technology, provide you the relevant cache metrics to provide you that whether your environment or your socket or cache is noisy or not noisy, based on which you can take a corrective action. Right, so there are quite a few use cases that we're looking into providing as a reference. And with respect to current gaps in the industry, right? So this is not just one instance of software, problems with one instance of software. It's more about how would you ensure as we move forward this type of closed loop automation can be easily applicable. Number one, telemetry tagging. So basically right now you do get metrics, a lot of them, but how would you associate with a particular container or a particular virtual machine? How would you indicate your workload is having so-and-so statistics based on which you adjust your workload? So telemetry tagging is an open area. That's a lot of conversations happening. And there's open metrics under CNCF. There's discussion ongoing. And then policy delivery and management across your VIM to NFVI. Now, you have a lot of policies across, for example, your ONAP layer. How does it translate to your individual node? How do you ensure those get supplied and it's good enough time frame that you can leverage the real-time or near real-time type closed loops? And then there's quite some work in ONAP communities, OPNAV, ETSI standards. Right, so there's zero-touch automation standard. There's ENI. I think it's Evolved Network Intelligence, I believe. So it's ENI. So there's a lot of work in standards and also open source communities in order to make the closed loop automation easier. So in summary, not just observability or monitoring is a combination of both of these play an important role in ensuring your service assurance. Telemetry plays a crucial role, and it's important to understand the various metrics available and not just take the default compute memory or your network stats. There's a lot more telemetry that can tell you the state of your application or your platform. And then there's various level of closed loops, and in order to provide the real-time, near real-time, there's ongoing work that you can leverage. Check out these open source communities, ONAP or OPNFV, to understand the work that is going on here. What is important is use case of interest. I talked about noisy neighbor, power savings, but what else are the use cases that might interest you to leverage closed loop platform automation, right? And the identifying the correct telemetry and the metrics plays a key role. So that's pretty much what I have. Any questions? Wow, it's very clear, huh? Great, awesome. Thank you.